How would you describe energy? It's one of those things that you kind of understand, but it's hard to put into words. It's like trying to explain what salt is. It's not really sweet and it's not really sour, but it's just kind of, well, salty. Energy is that same way. You kind of know what it is, but it's hard to put into words. You might understand that it sometimes involves motion or it can be stored, but what is it really? In this lesson, I'll talk about what energy is, and I'll give you a good definition for it that's easy to remember, kind of a gut feeling definition. And it will involve lighting this chip on fire. And I'll also cover one of the most important ideas in all of science, the law of conservation of energy. Most science books define energy as the ability to do work. But what is work? We'll cover that in this course. But if you don't really understand work in physics, then you won't really understand the idea of energy. And you need to be able to understand the idea of energy. But it's abstract. So I like to define energy like this. It's the ability to cause pain. So I'm going to take this chip and I'm going to light it on fire. There we go. It's starting to burn. Now some chips will burn better than others. This one's starting to go up. There we go. Get out your s'mores. We can have s'mores with our chips here. Be the perfect combination. So if I were to try to stick my hand into this, I can put it about right there just for a split second and then, boy, that's a little bit too hot. I don't want to do that. So this chip has the ability to cause pain. Where is that energy stored? Well, it's stored in the chemical makeup of this chip. And that's then released as thermal energy. I have here a bowling ball, and it has the ability to cause pain for this little rat guy. So that means it has energy. Man, it even broke off his ear. Ouch. We call this flavor of energy gravitational potential energy. Next, I'm going to show you a fan cart. It can also cause pain, so it also has energy. This is motion energy, which you probably already know is called kinetic energy. And finally, this finger rocket can cause some serious pain for our rat guy, which means it must also have energy. This flavor of energy is called elastic potential energy. Light can cause pain, like if a laser shines in your eyes or you look directly at the sun. Sound can cause pain if music is too loud or even during an explosion. And electricity can cause pain if you get shocked or struck by lightning. You starting to get the idea? All of these things can cause pain, so they all have energy. That's why my favorite definition of energy is the ability to cause pain. We can all relate to it and it makes sense. It makes this abstract idea of energy more concrete. I want to show you this really cool simulation. If we Google PhET here and go to their website, this is a website by the University of Colorado that has tons of simulations for all kinds of science and math things. We're going to go to Energy Skatepark Basics, which is an HTML5 simulation, which means you can run it in a browser and you don't have to download anything. We'll go to their intro page here, and I've got a skater on a ramp, just kind of a V-shaped ramp. And I want to throw in a grid here so you can see that he gets up to the same height each time. And if I add in a speedometer, you should be able to see that he is getting to the same speed each time, just past that halfway mark. And if I click on a different shape graph, it really doesn't matter what, well, not graph, track, it doesn't matter what shape it is, he still gets up to the same height beginning and end. So he's the same in the beginning as he is at the end, and the speed at the very bottom is the same as well. I'm going to go instead to the playground simulation because I think that's a little bit more fun. You can build your own ramp in any kind of shape that you want. You definitely have to check out this simulation. because it's just fun to mess around with. And you can learn a lot of cool stuff. This ramp I'm going to make less symmetrical. I'm going to make it steep on one side and pretty, I guess, not steep on the other side. Just kind of something like this. And I just want to show you that it's the same kind of deal. It doesn't matter what height you go to. Oh, I got friction on. I got to turn that off. That makes it more complicated, and we'll get to that in a different lesson. But we'll start right there, and it should get up to that same height over there, which it does. Speedometer, same kind of thing. Gets to the same speed at the bottom. Should be about right there each time. And then I can click on the bar chart for energy. It's going to keep track of the places that the energy is stored. The green is energy of motion, the blue is potential energy due to gravity. And you can see that energy is transferring back and forth between the two, but the total amount of those two added together is always the same, no matter where you're at on that track. That idea scientists call the law of conservation of energy. Or sometimes just they'll say conservation of energy. Pretty important idea in science. If instead of doing the bar chart though, I do a pie chart, which I kind of like better, notice that the size of the pie chart is not changing. So I have the same energy at the end of one ramp as I do at the end of the other side of it. I can go slow motion here, and you can see that when I'm at the very bottom, it's just almost all kinetic energy, and when I'm at the top, if I hit it right, it's all potential energy. But the total, the size of that pie chart, isn't changing no matter how we do it. So we are not creating any energy, we're not destroying any energy here, we are just transferring it around from one place to another. And remember, energy is the ability to cause pain, so if he were to fall off this ramp, oh say accidentally, boom, he could definitely cause pain. Pain for himself. Except this guy actually can never get hurt. He just lands on his feet every single time. Boom, that would be pain, but you know. There was a famous American physicist by the name of Richard Feynman who won a Nobel Prize, but he also was well known for his ability to lecture and explain things in really unique ways. And a lot of times they were things that were difficult to understand, like energy. And he said that there's this strange fact of nature that if you calculate a number and then nature does its thing, when you calculate that number again at the end, it will always be the same. That's the conservation of energy. And it's just an abstract thing that we don't really understand. He then came up with an analogy. So I've got here a picture of rooms, and imagine a young boy's room. Maybe it's like Dennis the Menace, and he has 10 blocks. And he has 10 blocks in his room at the start of the day, and when his mom tucks him in again at night, there must be 10 blocks again when he goes to bed. So 10 blocks. But she goes to tuck him in, and there are only 9 blocks. So the problem is we were missing a block. But she looks under the rug and realizes, oh, there really are 10 blocks, so we're okay. The next time she tucks him in, hopefully the next day, she looks everywhere, but there are only 8 blocks. She cannot find these missing 2. She even checks under the rug. So she gets looking, and the window's open. She notices 2 outside on the ground. So now we are back to 10 blocks, so everything's good. The next time she checks on him, there's 12 blocks. Now she knows he didn't have 12 blocks to start with. So she gets thinking about it and realizes his friend came over. She inspects the blocks and realizes that 2 of them look different. And so they were his friends, and we're back to 10 blocks again. Then Dennis starts to get even more creative. And so he now starts putting some of the blocks in his chest. And he gets really upset if his mom ever opens this chest where he keeps things. So she doesn't want to upset her son, so she doesn't look in the chest. But she wants to find out because she's curious and she's also clever. So she takes the chest and she puts it on a scale and weighs it. Figures out how much it weighs. She weighs a single block, figures out how much that is. Let's say it's 3 ounces. Then on a day when she sees that there are all 10 blocks there, she weighs the chest again and finds the weight of the empty chest. Then she can take the difference in those weights, divide by 3 ounces for each block, and figure out how many blocks were in there, just in case she needs that in the future to be able to weigh it to figure them out. So one day there's some more missing, and she realizes they must be in the bath. There's dirty water in there, so she can't see into it, but she thinks that they must be in there. And rather than to reach in, because she wants to be clever, she realizes that she can measure the water level, and by how much the water level went up, she can determine how many blocks must be in there. Well, this analogy that Feynman came up with has lots of important things for energy, lots of important connections. One of them is that energy can be stored in all of these different places, and sometimes we have to look pretty hard to figure out where that is. We also have formulas that help us calculate each of these places that energy is stored in. And when we take the energy before and calculate it, it's always equal to the energy afterward. But here's the interesting thing. There really aren't blocks in real life with energy. And the confession I have to make is, I can't really tell you what energy is because we don't really know what energy is. We know that it's a blob of something that makes something happen, but we don't really know what it is. It's not blocks, but it somehow is involved in motion and in potential energy and kinetic and all these different places that it can be stored. So I've given you a little bit of how you can think of energy, the ability to cause pain. I've also let you think about the idea that the energy before equals the energy of after, which is a conservation of energy. But you may be wondering, where else is this course going to go? What other questions are we going to hit? Well, here's one example. You may wonder, how much does the air resistance affect a Nerf dart? How much energy does it steal away? So we're going to address that question. We will also address the question of, what is the best bouncy ball? That one must be broken. And other bouncy things as well. How to build a homemade energy popper. A couple of other questions that we'll hit that have to do with energy. Walking up the stairs versus running up the stairs. You get to the same height, so shouldn't it require the same energy? But why doesn't it feel that way? Why does running up the stairs feel so much more difficult? And we're also going to tackle the idea of, what is E equals mc squared really about?